So good morning again, folks. What we're going to do today is, well, I'm going to start from orbital to say I'm going to pick up where we left off. We were talking about systems with viscous damping, right? I started talking about damping, what damping is, and I pretty much told you that I actually brought the slides from previous class. I'm going to do a quick review on those slides to make sure that we're all on the same page before we move forward. We got deep into some mathematical procedure, and then I had to stop because we had a quiz. So just want to make sure that this is some very short, refreshing. It's good for all of us. So I was talking about damping, right? First, I started by saying that any vibrating system has three elements, should have three elements. Right? An element that stores potential energy, which is spring. We saw it as a spring in a spring mass system, an element that stores kinetic energy, which was mass in a spring mass system, and in a pendulum is the inertia, and an element that dissipates the energy. Obviously, all systems, or better to say, no system moves forever, right? They'll stop at some point if there is no external force or external source of energy continuously feeding energy into that system. If there is no such source, any moving system stops at some point. Now, I said, well, specifically, we're going to talk about viscous damping, at least for now. Later on, we'll talk about a different type of damping that is related to friction. Now, I said viscous damping is the most common damping we're going to see. It happens when a system is in a fluid medium, depending on what type of fluid. Obviously, the amount of damping changes. You're in oil, gas, water, air. Pretty much any system moving within a fluid medium has to deal with damping. If you think about it, a very viscous fluid obviously has higher damping. It's very hard to move something within a honey, right? If you think about honey as a very viscous fluid, as opposed to water, right? It's a little easier, or air is much easier. So the amount of damping you get depends on the fluid medium properties, at least. There are other factors involved too, but that's one of the important ones. Now I said, well, let's focus on viscous damping there. And I said, well, for a viscous damper, the force of damping is, there is a relationship between the force of damping and the velocity of the system vibrating within that fluid medium. If you want to form an equation for that relationship, I said we use a constant, which is called damping constant, with the unit Newton second per meter. Right? We call it C in this course. Later on, we'll see when I do simulation in Modelica language or Open Modelica specifically. They use a different notation, so hopefully that doesn't cause confusion. But in the course, we use C for damping. You might see different letters in different places, different textbooks, but the typical way of referring to it is using letter C. Now I said, well, let's start where we always start, with the simplest possible system with these three main elements that I said every vibrating system has. Right? So mass, as storing potential energy, kinetic energy, spring, storing potential energy, and now a damper. And I said we represent a damper with that icon that I put in a spring mass damper system. That's a typical way of the symbol for viscous damper. So I draw free body diagram. It said, well, here is the equation of motion for, right? Here is the equation of motion for a spring mass damper system. This one, right? Now it's different. It's still a second order linear differential equation, and it's homogeneous, but now we have x dot in our equation as opposed to what we had for a spring mass system, which we only had x double dot and x. So this means that this equation is not similar to anything we had before. So we have to actually solve it again. Keep in mind, we always start with the simplest system, solve the equation of motion, find the system response, and then later on you'll see we pretty much can convert any system that we are studying, as long as the type of damping is viscous damping, into a form that is very similar to this equation of motion. We're going to have, again, equivalent of mass, equivalent of stiffness, and equivalent of damping. And we can use the system response. And that's why we start from a simple system when we spend good amount of time on a simple system, because pretty much anything else later on, we are able to convert it into this type, this equation of motion, and use the whatever we get for this system for our analysis. Now, from there, well, I was saying this is the second order linear differential equation, right? I said, well, to solve this, depending on how much you remember from differential equation, the course, might not be that much, I'm guessing, most of you, which is, I don't blame you. It's been a while and you had different courses. To refresh your memory, I said, well, typically what we do, we form the characteristic equation and we find the roots for that characteristic equation. And depending on what those roots are, we can decide what is the general form of the solution for this differential equation with a couple of constants, and we can find those constants using initial conditions for this system. In this case, we're talking about initial velocity and initial displacement. Now, so I formed the characteristic equation. I found the equation for the roots, lambda 1 and 2. There are two roots for this, right? It's a second, it's a quadratic equation. I defined two things before I move forward. I defined critical damping, CR, which is 2m omega n, 2 square root of mk. So critical damping can be found, and it's independent from the value of damping constant, C. So you don't need to know that. You can just find critical damping by knowing mass and the stiffness of the system. And I defined damping ratio. Now it's the ratio between the damping constant and critical damping you found. So if I use these two definitions and plug them back into the equation for the roots, which is the equation for lambda 1 and 2, here lambda is just a constant. We'll get, well, constant as opposed to x dot, x double dot, and xt. It's not a function of time. If I plug them back, I'll get the equation for the roots of characteristic equation, the last equation at the bottom of this slide. I said lambda 1 and 2 is minus zeta omega n being natural frequency, square root of k over m, plus minus omega n, the square root of zeta squared minus 1. Now that plus minus means with plus we get one root, with minus we'll get another root. Now I said, well, here is the equation for the roots for that characteristic equation. As I said, depending on what roots do we get, the form of the general solution changes. Now, zeta squared minus 1, we specifically focus on the components we have under the square root. Here is zeta squared minus 1. Now, depending on what that is, right, we have a square root. So the outcome of this whole thing could be either a complex number, could be a real valued number, or, you know, zeta squared minus 1 could be 0. So we have three cases. Zeta squared minus 1 can be smaller than 0, which gives us a negative number under this square root, which eventually lambda 1 and 2, the roots become complex numbers. Zeta squared minus 1 can be 0, or zeta squared minus 1 can be greater than 0. Greater than 0, then both roots are going to be real valued numbers because we just get real values. Now, I said depending on which one we have, the type of response we get from this system changes. So I started from the first one. I said, well, if zeta squared minus 1 is smaller than 0, right? And I call this underdamped. Why? Because if you go from zeta squared minus 1, right, from there, go here, you can get, well, zeta is C over C critical, meaning that C is smaller than C critical. So meaning that the damping constant is smaller than the critical damping, the value of critical damping. So we call this underdamped. Now I defined something else. I generally defined three things in last class. This is the third one. I defined damped natural frequency. Now damped natural frequency is related to frequency, the natural frequency. This is important. The unit is still radian per second. But I define it as omega n times square root of 1 minus zeta squared. Now you'll see why I define this, because now using this, in this specific case when zeta squared minus 1 is smaller than 0, I can rewrite my roots. for characteristic equation, which I did. I said lambda 1 and 2 is equal to minus zeta omega n plus minus omega n. Now for that square root of 1 minus zeta squared, right? Well, it was square root of zeta squared minus 1. I factored out 1 minus 1 because zeta squared is smaller than 1. I wanted that square root to be always positive, and I took that minus 1 out. Square root of minus 1 is I, it's a complex number. So the whole thing, now we have a set of roots, two roots that are complex conjugate, like these are complex valued numbers. Because we always know that omega n square root of 1 minus zeta squared is positive, and we put the I out, as long as we are in this case, which is zeta squared is smaller than 1. Now, after all these rambling, I would say, since we have these roots from the differential equation, it tells us if the roots are like this. If you have roots that are complex valued and they're complex conjugate like these, the suggested solution is in this form. Xt is equal to a e to minus zeta omega nt sine omega dt plus phi. This is the suggested solution, like the suggested solution I gave you for a spring mass system. Now, our task is to find the constant values in this in suggested solution using initial conditions. Now, two initial conditions, I said, well, x at t equals to 0, a sine phi, x dot as t equals to 0, right? Initial position, initial velocity. If you plug these in, I took derivative with respect to time here, right? The last equation at the bottom of the slide. From this suggested solution to be able to plug in or find x dot at t equals to 0. So I got two equations. One from x dot naught is equal to that equation, and the other one is x naught is equal to a sine phi. So mathematically speaking, I have two equations, two unknowns. So I should be able to find these two unknowns, which are a and phi. Right? The amplitude, if you remember, and phi is the phase. Anything else, as long as we know the system characteristics, including mass, stiffness, and damping values, we are good and we can find those. A and phi depend on initial conditions. So I continued from there. I said, well, let's use those initial conditions, right? What I did was, let me go back there. I divided the one at the bottom, x naught dot, by the one at the top, x naught. And obviously divided whatever was on the right side of each equation. So from there, I could find the equation for phase, and it's phi. And it's you can see it's the function of system characteristics, which you can find by knowing m, k, and c. You can find omega d, omega n, zeta, and initial conditions, x naught and x naught dot. So that's phase. Now, that's where we stop. Now, we're going to continue this by trying to find the a value, the value of the amplitude using initial conditions. So let's take a look at how can we do that. Now I'm going to do a trick, right? The same way I did a trick by dividing those two to find phi. To find a, I'll say, well, I know what phi is. This is the value of angle phi. Now, I can say this phi can be part of a right triangle, right? Be with me a little bit here. So let's say if it is a right triangle like this, and this is phi. Now, if this is phi, tangent value of phi is x naught omega d over x naught dot plus zeta omega n x naught, which means I can think of this as this side being x naught omega d and this side being x naught dot plus zeta omega n x naught. Because if this is phi, then phi would be tan inverse, is opposite over adjacent, right? X naught omega d over x naught dot plus zeta omega n x naught. So why am I doing this? Well, if you go back to initial conditions, x naught was equal to a sine phi. So from the first initial condition, I can say A, well, let me write it here. X naught, we had it as A sine phi. So from there, I can say A is equal to X naught, or let me just write it this way, 1 over sine phi X naught. I just took sine phi here. Now, here is the trick, and the reason I draw that triangle. Now I can find what is sine phi. Right? If this is the triangle, I know phi based on those two sides, and it's a right triangle. All I need to do is to find sine phi from this triangle. So sine phi, what is sine phi? I have a technical problem here. Sorry, guys. Don't give up on me yet. I'm trying to find out what the issue is. The computer just gave up on me. Almost there. Let's see if I can fix this. Let's give it another shot. Okay, sorry about that. So sine phi, it's just a little delayed. Sine phi would be, well, whatever we have. What is sine phi here? Can someone tell me that? Well, I know two sides and I know phi. If I know those two sides, what is the value of hypotenuse? Would be X naught omega d squared plus X naught dot plus zeta omega n X naught squared. Right. Hopefully nobody disagrees with it. So right triangle, I know two sides, I'm finding the hypotenuse. So what is sine phi now? Any comment?
Would it be X naught omega d over the hypotenuse?
Yes, exactly, Chris. Thank you. So it's going to be X naught omega d divided by the hypotenuse. X naught omega d squared plus X naught dot plus zeta omega n X naught squared. Now I can just easily plug this back into my equation for A. Right, I just flip it. So I'll get A is equal to, I flip this and X naught, this goes to the bottom, you'll get square root of X naught omega d squared plus X naught dot plus zeta omega n X naught squared divided by omega d. And this is the value for amplitude. This is going to be amplitude. So as long as you know the system's characteristics, M, C, and K, and no initial conditions, you can find everything here. You can find zeta's damping ratio, C over C critical being 2m omega n being the square root of K over M. So everything can be found. Right? You can find omega d by knowing omega n. Omega d is equal to omega n times the square root of 1 minus zeta squared. We can find amplitude. Now, as we will see over and over, we don't like long equations. They don't tell us that much. We're looking at these values for A and phi, and keep in mind these are the values that you need to plug in for the system response. So the system response, let me just add it here. So xt is A e minus zeta omega n t sine omega d t plus phi. And that would be your system response as long as you can find, as long as you know phi and A from previous equations. So system response. That's how your system respond to some given initial conditions. Now, as I was saying, that we don't like long equations because we can't really see what is going on there. It's just too many things in one equation. I know x naught dot, zeta, omega d, omega, and we don't even know what is going on there, how things change by changing one thing or the other thing. What we love is graphs. So let's plot this system response and see what does it look like for a system with a spring mass damper. For a spring mass damper system, what does it look like, the system response? Let me bring the figure because I realize that I probably can never draw it the way I should. Here's the response. There we go. So if I plot that response, xt, this is xt, this is time, right? A second, xt depending on what the unit is, meter, millimeter, centimeter. This is your system response. All right, let me just write it here. System response. Now let's take a look at see what we can identify in this system. First thing is the distance between these two peaks. What that is? Can someone guess?
Is that the natural frequency?
Well, related to natural frequency.
It's the time period.
It's time period, right? But this time period is a time period for a damped system. Keep in mind. Because this is 2 pi over omega d. Omega d is the damped natural frequency. It's different from omega n. Now, can someone tell me this TD is smaller or larger than T? Or let's rephrase that. If you have two systems exactly similar, you add, if you have a spring mass system, it's oscillating, and you know it's time period. If you add damping to that system, does that time period increase or decrease? So I'm going to repeat the question. I have a spring mass system oscillating. I add a damper to it, a viscous damper. What happens to time period? Is the time period longer or shorter for comparing these two systems after you add a damper? Now, to answer that question, look at where omega d is. Omega d is at in this fraction is the denominator, right? And keep in mind what omega d was. Omega d, I defined it as omega n square root of 1 minus zeta squared. Right? And zeta is smaller than 1. So for an undamped system, T was 2 pi over omega n, right, when we had no damping. For damped system, 2 pi over omega n. Now for damped system, time period is 2 pi over omega d. Right. Omega is in the denominator. So let's start from here if you still cannot follow. Which one is higher, omega d or omega n, for an underdamped system? Look at natural frequency and damped natural frequency. Which one is a bigger number? Waiting.
Is it the natural frequency?
Natural frequency is bigger, yes, because we have zeta, which is smaller than 1. So this part here, whatever comes out of this square root is, let's think about it, 1 minus 0.5 squared. Right? It's a number smaller than 1. So you're multiplying omega n by a number smaller than 1. So omega d becomes smaller than omega n, always for an underdamped system. Now, knowing that, if omega d is smaller than omega n, Let's go back here. What about time period?
It will increase.
It will increase, right? Because omega d is smaller now. So given two exact similar system, one with and one without damping, the one with damping has a longer time period. These are the reasons why we derive the equations and look at the equations and system response. We want to get insights about systems. When you design something, right, you want to know what happens if you add damper. You don't know the equation at the moment, you don't memorize these equations, but you need to have these insights. And these insights are coming from solving these equations. That's why we use math and we look at the system response and these complicated equations, because we want to know how does system behave, or how does that behavior change under different circumstances. Right? We are looking for insights. Okay, what else on this graph? We have, we have X naught here, right? Wherever the system is at the beginning, it's the initial displacement. Another thing is if you connect these peaks together, these peak values, I'm gonna get a curve. I'll do my best to draw it. You get a curve like this. The equation for this curve is a e to minus zeta omega n t. It's an exponential decay part of the system response. Remember, system response was, what was it? It was xt a e to minus zeta omega n t sine omega d t plus phi. The part that exponential, that causes the exponential decay, well, you'll get that part by connecting these peaks. Anything else? Let me make sure that, okay, let's put a couple more things that I did for undamped system. If we continue this line, well, we don't have negative time, but hypothetically, if we can continue this line, this area or this gap here, this distance on time axis is phi over omega d, similar to phi over omega. What else? We know these parts, these points here, this point here, this point here. These are where we have the maximum velocity. This is equilibrium point. If you think about the spring mass system oscillating, this is the support. It starts from equilibrium point, goes back and forth, goes all the way to the end, it stops, changes direction, comes all the way to this side, stops, changes its direction. Every time we pass this equilibrium point, this is where we have the maximum velocity before it starts slowing down. So these are where we have maximum velocity. We pass the equilibrium point. X is 0. Then it becomes positive, negative, positive, negative. This is X. X is equal to 0 equilibrium. I think that's pretty much it I want to talk about. So every time you're given this plot, you realize that I love plots, I love graphs, because they, for lack of a better word, plots talk. Equations don't talk. They don't tell you that much. You look at this, you see things about the system, how things change. But look at the equations, so many things going on. You don't know. It's hard to interpret those equations. And the same story about if you want to find this velocity, velocity of the system would be d dt of the system response. You know it by now. Acceleration of the system, right, would be the second derivative with respect to time of the system response. So as long as you know the system response, you can find its acceleration, its velocity. I think that's all I wanted to tell you about this graph. So that is an oscillatory system. This was for the situation that the damping or critical damping is smaller than critical damping. C is smaller than C critical, meaning that the damping ratio zeta squared is smaller than 1. Right? That was case 1. Remember, this is case 1. Here is the case 1. Now let's continue. Right? We said, well, characteristic equation or the roots or the suggested solution for this system depends on the type of roots we get. And it says zeta squared minus 1 is one case that the roots change or dictates what the roots are. The second case, right, would be zeta squared, let me follow the same, zeta squared minus 1 greater than 0. Now from there, right, let me use proper color. Zeta squared is greater than 1. Right? If we ignore the negative part that we don't care, zeta squared is greater than 1. This means, well, zeta squared is, or zeta is C over C critical. This means C is greater than C critical. Damping of the system is greater than the critical damping. So we call this overdamped system. It's overly damped. We added too much damping to it. Now the damping is way more than critical damping. Now, if you do this, right, you get the roots. Well, the roots are going to be real valued. Is minus zeta omega n plus minus omega n square root of zeta squared minus 1. Remember, this was the general form of the roots. Now, zeta squared minus 1 is greater than 0, so that the square root gives you a positive value here. All right? Let me see if I can find it better. This is always positive now. So this is just a set of real valued roots. Now, if these are real, if the value of the roots or the roots are real valued, the general solution, I'll just give you the general solution with the coefficients. We're not going to solve that one. The suggested solution, or general form of the solution, would be xt is equal to e to minus zeta omega nt. Let me write it somewhere that we have more room. So let me put it here. Suggested solution would be xt is e to minus zeta omega nt multiplied by d1 e to minus omega n square root of zeta squared minus 1t plus d2 e to minus, or plus in this case, or just nothing pretty much, omega n square root of zeta squared minus 1t. This would be your general form of the solution, or this would be the system response. Keep in mind, this is the system response when we have an overdamped system. System response. What are D1 and D2? Well, again, from initial conditions, we can find them. But I'll just give you the general form. It's relatively long. So D1 would be minus x naught dot plus minus zeta plus square root of zeta squared minus 1. And this whole thing multiplied by omega n x naught divided by 2 omega n square root of zeta squared minus 1. This whole thing is just D1. And you can find it again by knowing the system's characteristics, remember. As long as you know MCK and initial conditions, you can just find it. Doesn't matter how long it looks. Everything you need, you should be able to find by just knowing those. And similar to that, but in this case, just to get rid of the negative value, and I believe negative value here. I have to double check these equations, but zeta squared minus 1 omega n x naught divided by same denominator, zeta squared minus 1. So this is your system response, and this system response, I try to put something around it. I don't know if I made it better or worse. This is your system response, where D1 and D2 are two coefficients that can be found from these equations, D1 and D2. Now, as an example, if you just want to get a sense of what happens when different, conditions, for different conditions in the system, let me see if I can fit that here. Let's say I have this, and I have this. Just want to plot the system response for some examples. So xt, and this is t, time. I'm going to plot it for when, let me use a color that we haven't used. So first one I did, I said, well, let's say if x naught dot is 0, so initial velocity is 0, and x naught is greater than 0. So some situation that velocity is 0. So velocity is 0, meaning the slope should be 0. X naught is greater than 0, so I'm above this horizontal line somewhere here. All right, this system response looks kind of like this. Keep in mind, this is non-oscillatory. The system is not oscillating anymore. It's overdamped. Another example would be, let's say we have, what else did I do? I said, well, let's say x naught dot is greater than 0, some initial positive initial velocity, and x naught is 0. So initial displacement is 0, so I'm going to start at 0. Velocity is not 0, so there is some slope. Right? I'll draw it like this. The last example I did here, I did x naught is 0. Let me be. X naught dot is 0, and x naught is negative. Like initial displacement is negative. So we'll see the same situation. The beginning, it starts from here at the bottom because x naught is 0, and the slope should be 0 because the initial velocity is 0. So we'll get something like this. So system does not oscillate. You know, whatever input you give to it, push it, give it initial velocity, some initial displacement. Think about the spring mass system. It goes to one side, and it slowly starts coming back towards the equilibrium point. It's overdamped. Now, a very good example of overdamped system I can give you, you can imagine, is in the department of doors, specifically like a bathroom door. If you think about the bathroom door, now at the top there is a system of damping and spring and damper there. Now, but the damping is very strong. So you've noticed it doesn't matter how hard you push that door is not going to oscillate going back and forth. That door is going to go like as hard as you push it goes to somewhere, you open it, and then it slowly comes back to where it was. Even if you want to pull it back, sometimes you can because it has to go through the process because it's an overdamped system. It doesn't oscillate. There isn't a spring there to push the door back to where it was, but it's overdamped to make sure that when you open it, it doesn't come back to your face, right? So it slowly comes back, like these graphs I put here, slowly comes back towards its equilibrium point, where the door is closed. It's an overdamped system in a design. Now, the last case would be when we have, third one, when we have zeta squared minus 1 equal to 0. Right. Now, in that case, let me get the right color. In that case, well, zeta squared is equal to 1, ignoring the negative part. Zeta is equal to 1, meaning that C is equal to C critical. Damping of the system is exactly equal to the critical damping. It's a very specific case. Right? It's the exact number, these two numbers are exactly the same. Hard to achieve, obviously. And this is called, for that reason, this is called critically damp. I can do better. Critically damped system. Because these two values, the damping constant I put in the system is exactly equal to critical damping. Now, what happens is that, well, roots were lambda 1 and 2 minus zeta omega n plus minus omega n square root of zeta squared minus 1, right? What happens to these roots? Can someone tell me what happens here?
You go to 0.
Roots become 0. So zeta squared minus 1, zeta squared is 1, right? So zeta squared minus 1 becomes 0. We have a 0, but not roots. This becomes 0.
Would it just be the natural frequency?
Exactly. So it becomes this minus natural frequency, minus omega n, because this is 0. The first term, zeta is 1. Eventually you get just minus omega n. So think about differential equation. Now you have a second order differential equation that its roots are the same. You have two similar roots, repetitive roots. So the suggested solution, I can just actually put it here. Suggested solution, which is your system response for this case, when you have a critically damped system, becomes xt is d1 plus d2 t e to minus, I would say, omega n t, because zeta is, let me do better. Zeta is 1, so it becomes minus omega n t. So this becomes your system response. Let me follow the same process. This is your system response. That's how your system responds to given input. And D1 and D2, I'll just give you the values. You can find them, as always, using by plugging in the initial conditions and find these values. D1 is very easy, is X naught becomes equal to initial displacement, and D2 is equal to X naught dot plus, I guess it's plus, omega n X naught. These are the coefficients of D1 and D2. So as long as you know system's initial conditions and its characteristics, you can find the system response. How does that system respond to any given input? Which is what we wanted. We want to know what happens in a system if it's under different initial conditions, given velocity and displacement. So I'll do the same thing that I did for previous example, previous case. If I plot it for some cases to get a sense of what is going on, I did X naught dot greater than 0 and X naught, I just put it for some specific number. I guess I got this from textbook. So X naught is equal to 1. Just want to get a sense of how things work. If this is 1, we have some initial velocity, meaning that we have to have some kind of slope at the beginning. This is xt. And this is time. So we start from 1, it's initial position. We have some initial velocity, and then the system goes like this, goes towards equilibrium point. See that this is also not an oscillatory motion. We don't really, we are not going to see an oscillation. You will see, you might ask what's the difference between critically damped and overdamped system. You will see how fast the system comes back to its initial position or equilibrium point is the difference. So let's just finish this. I'm going to put everything together at the end. So this one, let's say for the second case, I said, well, what if X naught dot is equal to 0 and X naught is equal to 1. So start from the same place. This time velocity is 0, which means the slope of the line at the beginning should be 0. Velocity is the slope of the displacement, right? Derivative of displacement. So let me see if I can draw it. So it goes straight and goes like this. Last case, I don't even remember which color I was using previously. Let's just go with this. And if x naught dot or velocity is negative and x naught is 1, so we're still going to start from the same place. The only difference is the velocity is negative, so the slope is negative. So I'll get something like this. Symptotically approaches 0. Now, we looked at 3 cases, still one system, depending on what is the value, keep in mind. All these, which solution you choose, what system response you go with, depends on the value of damping, C. Right? And how does that relate to C critical? Whether it's equal to it, greater than that, or smaller than that. Now, I want to put all these 3 systems in one plot. As I said, plots, graphs, talk. Equations, confusing, not clear. So I'm going to put all of these in one plot. I want to compare these systems to get a better sense of what is going on. Now, let's start with what we had from before. This is undamped system. Remember that. This is a spring mass system with no damper. It just oscillates continuously with no energy dissipation. Right? The amplitude stays constant. Now, as opposed to that, or not as opposed to that, the next case we started with is when we have underdamped system. Underdamped. Meaning that when zeta is smaller than 1. All right, so hopefully I have the plot here for myself. So zeta is smaller than 1. You will see obviously the system response slightly, slowly decreases. Right? The energy is dissipating. We have a damper. The motion is slowing down. Now, looking at the green one and the red one, they both approach 0. One of them is approaching 0 faster than the other one. All right? Now, the one that is approaching 0 faster is critically damped system. Right? This one. Critically damped, meaning that zeta is equal to 1. And the other one is overdamped system. When zeta is greater than 1. So when you're designing a system that you want that system to come back immediately to its initial position like that bathroom door, the ideal case is to have a critically damped system, right? Because it gets there faster than overdamped system. Why not just going with that? I always prefer this is x, t, and this is time. However, the problem is it's very hard to design a system that is critically damped because that value of C that you put there is just a constant, a damper, like a dash pot. Is another name for viscous damper. They call it dash pot. Sometimes you'll see that. Well, it's a fixed number, but system, characteristics change a little bit. Mass, stiffness might change, over using the system. So that C is not going to stay exactly equal to C critical. What if C becomes smaller than C critical? Then suddenly you're going to go from a critically damped system that comes back to its position without oscillating to a underdamped system, which is oscillating. And that's what you don't want. You don't want a bathroom door that goes back and forth. That's actually dangerous. So we always tend to, in most designs, we always tend to do an overdamped system design to make sure that even if things changes a little bit, it is still doing what we want. No oscillation. Okay. I want to do an example, simple example. Any question up to here, guys? So we do, we'll see again, we'll see later that I'll talk about dampers in series and parallel. Well, same situation we had with spring mass systems. Right? We simplify every system into the general form of the equation of motion, mx dot double dot plus cx dot plus kx. and find the equivalent of mass, stiffness, and damper, and use that to study the system, because now we know the system response and the solution to equation, that equation of motion. That's why, again, we start from very simple systems. Now, an example, very simple example, I just want to show you where to start when you're dealing with these systems. We have a spring mass system that, let's put it this way, spring mass damper system with M is equal to 1 kilogram, C is equal to 5 Newton second per meter, and K is stiffness is 16 Newton per meter. Find the system response for initial conditions that are given as x at t equals to 0 is at 0.1 meter, system starts oscillating from here, and x naught dot at t equals 0, initial velocity is 2 meters per second. So where do we start? That's the usually question. That's the hard part. We have to decide what kind of system we're dealing with. So we have to figure out what is the relationship between zeta and 1. Is it smaller than 1? Is it greater than 1? Or is it equal to 1? Or one step further, you want to know the relation between C and C critical. We know C is 5 Newton second per meter. We have to find C critical. C critical is 2 m omega n. Right? I can just write it directly as 2 square root of mk. So 2 square root of m, well, m is 1 kilogram, and k is 16. So square root of 16 is 4. This becomes 8. It's a damping, so Newton second per meter. So we have the value of critical damping. We have the value of damping, right? That's where we start. You want to know what type of system. Is it critically damped, over damped, or under damped? So since, what kind of system is this? You guys tell me. What is the relationship between C and C critical right now?
Our C is less than C critical, so then this would be underdamped.
Exactly. Dominic, right? It was you?
Yeah.
So C is smaller than C critical. Right? 5 is smaller than 8. So we have an underdamped system. The rest, we know what to do. Right? We just find all the parameters we need to find the system response. Right? The system response was, let me, if I remember, was xt a e to minus zeta omega nt sine omega dt plus phi. So here is the stuff I need to know. I need to find omega n, I need to find omega d, I need to find zeta and a and phi to be able to form this system response. So let's get started. Omega n is the square root of k over m. So square root of 16 over 1, this is 4 rad per second. Now, I know C critical, so zeta, or damping ratio, would be C over C critical. C is 8, C is 5, C critical is 8, 5 over 8. If we have the number. It's 0.625. Has no unit because it's a ratio of between two dampings. So I found omega n, I found zeta, I can find omega d, or damped natural frequency, would be omega n square root of 1 minus zeta squared. I have omega n as 4 multiplied by 1 minus 0.625 squared. this will give you 3.1225 rad per second. As expected, obviously omega d should be smaller than omega n for an underdamped system. So I know omega d, I have to find A and phi now. So A, what was that? Was, see if I remember, x naught omega n squared plus x naught dot plus zeta omega n x naught squared. One of them should be omega d. Omega d. The first one is omega d. Divided by omega d. Let me double check I put the equation right. Yeah. So if you plug in, you know what x naught is, you know what x naught dot is, you know now what the value is of omega d and zeta, you'll get 0.7275 meter. And I can find phi as well. Tan inverse x naught omega d divided by x naught dot plus zeta omega n x naught. Plug in the values, you know everything you need. You already calculated that. Phi becomes 0.138 radian. So you plug all these in back into the equation of motion, right? This is, system response. So once you plug this back, you will get xt is equal to A, which is 0.7275 e to minus zeta, which is 0.625 times omega n. Did I do the math? I got 2.5 minus 2.5 t. Hopefully I didn't make a mistake. Sine omega d, which is 3.1225 t plus 0.138. And that would be the system response. So you always start from what type of system you have by looking at the relationship between C and C critical, right, with these kinds of problems, and then take it from there. The rest is just plugging in the values. Let me stay here if you're taking note. Now, I think the last thing I want to talk about is the same story we had with systems, a set of dampers. Let me just make sure that, okay, this is good. A set of dampers. Right? What happens, you know, the same story we had about the springs, that they're in series or in parallel. What do we do? How do we deal with them? The same story here about dampers. Right? So I'm just going to put them here. So I'll put it under damping or dampers configuration. Dampers could be in series or in parallel. Right? Let me start with in series. In series, right, meaning that, well, if I have a set of dampers like this, did I number them? Yeah, let's just start from a wall. Let's say it's damper 1, damper 2, or you can do better. Let's use C1, C2. C1, C2, C3, up until Cn, and let's say it's connected to a mass, right? Somewhere in mass. For now, just forget about the spring. I just want to look at the dampers. Now, the equivalent for this, we can find the C equivalent, or just one damping that is equivalent to all these dampings in series, is 1 over C1 plus 1 over C2, 1 over Cn. And that would be summation of all dampers from 1 to n. Right? As long as the dampers are in series, you can find this. And this is pretty much equivalent of this system, right? What we are doing is that we are finding the system equivalent, just a simple damper with the C equivalent. And that the value of C equivalent is this value. Now they can be in parallel. We said when the dampers are in parallel, meaning that they have the same story about springs, similar. How do we identify dampers in series in parallel? We said when they are in parallel, they have the same displacement. In this case, they have the same velocity. So if I have a set of dampers, let me draw it here. If I have a system, this is damper 1, a very ugly damper. Here is the damper C1, and then I have the second damper C2, third damper C3, and it goes all the way to Cn. Now with all these dampers, let me try to use some tools, makes my life easier. Now let's say they're all connected to the same mass, right here. We're talking about one system. Now, all these dampers, if you think about the free body diagram of this mass, like Cx, C1x dot, C2x dot, C3x dot, all these forces are trying to take the mass back to its equilibrium point, to the left, if it's moving to right. So they have the same velocity. So equivalent of this is a system like this. And this is C equivalent. And the value of that is pretty much just summing up dampers. C2, Cn, depending on how many you have. So C equivalent is summation of Ci, I from 1 to n. Right. So if you have a system with multiple dampers and different configurations, you just have to find a C equivalent. And then I cannot emphasize this more. It always creates confusion and problems during the semester. I'm saying this now, I'll keep repeating that. Once you find the equivalent of a value, right? Now we have a new system, spring damper, let's say there's also mass damper, let's say there's also a spring there. Now instead of C, please pay attention to it. Instead of C, you have C equivalent. So whatever we found from before, right? All this calculation we did, these C values here, like this C, what else? This C here, any calculation we did using C, now you have to use C equivalent. Forget about that C. Now you have C equivalent. Everything should be done using C equivalent. Is your system overdamp, underdamp, or critically damped? Depends on the relationship between C critical and C equivalent now. How can you find damping ratio? C equivalent over C critical. That zeta should be zeta for the equivalent system. Keep that in mind. Okay, I'm gonna throw a curveball, give you an example. Right? I'll post a solution to this example, but I'll just write this example here, and it's pretty much similar to what we had before. If we have a bar like this, we looked at this bar situation when we had the springs. Now, the same story, we have a bar rotating around point O. We have a spring here, and the stiffness of this spring is K. Now, instead of a spring on this side, we have a damper there. So this is C. The bar, I'm going to give you the distance. The full length is L. This is L over 4. And this is 3L over 4. And the bar is rotating around point O. Right? This is point O. Now, you are asked, well, don't forget these assumptions, theta, or let me write it this way. Rotation about point O, by that I mean theta, is small, and system starts oscillating from the equilibrium point. Put it here. Can someone tell me why do I need to put that? Start from the equilibrium point from here. Can someone tell me why that condition should be there? Theta, well, first start from here. Can someone tell me why the condition of theta small should be there? When do I throw it there? Under what condition, what kind of assumptions do I want you to make when I tell you that theta is small?
You want us to assume that your cosine theta is about 1 and then that your sine theta is about theta?
Exactly. Thank you. Exactly, Cindy. Was Cindy, right?
Yes.
So exactly, that's the one. Now, why do I have to put the system start oscillating from equilibrium point? Why do I have to put it there? Can anyone tell me why that has to be there?
Doesn't that define an initial condition that x dot 0 is 0?
No, I'm actually gonna, I think I gave you initial conditions. Or I don't want you to find the system response actually for this. But no, the reason I say this system starts from equilibrium is you can safely ignore the effect of weight. Go take a look back at the example we did as a spring mass system. I said, well, let's assume that it doesn't start from equilibrium. Let's assume we add a mass, it's stretched, and then well, we were assuming that the oscillation starts from equilibrium, but we said, let's just go step by step. Add a mass, let this stretch, the spring, and then give it some initial velocity or displacement from that point. And we took the weight into account and realized that as long as the system starts from equilibrium, we can safely ignore the effect of weight. So when we draw the free body diagram, as long as the oscillation starts from equilibrium, we say, well, ignore the weight. So with this bar like this, if it is in horizontal position, but it already, this is spring, it already is stretched a little bit, right? This is spring here. It's already stretched a little bit, or sorry, compressed. And it canceled out the effect of weight. Now we're in equilibrium position. Now we start the oscillation. So we know that if you start from equilibrium position, the initial stretch or compression in the spring takes care of, you can think about it that way, the effect of weight. And we don't have to be worried about that initial compression or stretch in the spring, as long as the oscillation starts from equilibrium. If it doesn't, different story. Like the spring mass system, we have to take into account that how much the spring is stretched or compressed because of that initial effect of weight. So this has to be there, so you can safely ignore the effect of weight, not the effect of mass. Mass has an effect as an inertia in the equation, like I theta double dot. Weight is just the force. So don't get these two confused, please. You still have the effect of mass, because the inertia it creates. You don't have the effect of weight anymore. Don't have to be worried about gravity. Let's put it this way. So what I want you to do is that I want you to find the natural frequency, find the natural frequency find the damping ratio and finally I guess that's pretty much it. I asked you to find natural frequency and damping ratio. Everything is parametric. I didn't really give you the numbers. I'll post a solution to this. I'll just add the solution to the same slide and post it. But I want you to go and think about this. You know, you draw the free body diagram like the same way we did for the spring bore. We do 2 springs. Find the values of how much the springs are compressed. The spring is compressed and the damper is compressed. In this case, you have x dot instead of x. And find the moments about 0.0. You have to find the mass moment of inertia about 0.0. Remember, a ball rotating around a specific point that is not exactly on the center of gravity, etc., etc. And you can find, you're going to end up having an equation, something theta double dot plus something theta dot plus something theta is equal to 0. Right? And then this would be your equivalent of mass, this would be your equivalent of stiffness, and this would be your equivalent of, sorry, the equivalent of damping, and this would be the equivalent of stiffness. Now from now on, when you want to find the system response, you use equivalent of mass, equivalent of a stiffness, equivalent of damping. Right? You use, for instance, C critical is 2 square root of M equivalent K equivalent now, because you have a new system, an equivalent system. Zeta would be C equivalent over C critical. Omega n would be square root of K equivalent over M equivalent. This is something that is a mistake that happens a lot, so I wanted to emphasize this, and I'll post a solution to this problem. Okay, we are done. Any question, guys?